Okay, good morning, everyone. Any feedback on the last tutorial? Did you find it followable, or was too fast, too slow, or? Yeah, this tutorial, we are going to continue with the same technique, that is method of equation. So just this is to get an idea whether we have to start from a basic example again or from intermediate. Do you want us to start from scratch, or? It's absolutely okay. I mean, that should be usable for you. Basic? Yeah. What about you, Fergus? Art? You want us to start from simple or medium or difficult? That would be the same method of equation from last tutorial. If you find the previous one difficult to follow, that would be reasonable to start from something simple. Simple? Okay. Same with you, Ivan? Yeah. Okay. Okay, now I have Yonging joining the online session. Hello, Yonging, how are you? Thank you. Just trying to share my application screen. Something is not working. I have to rejoin the session. Sorry, just bear with me. I have to rejoin the session. Let me read your note. For some reason, I'm not able to see it. Okay. So this is regarding the internal load inside the beam structure. So I think everyone knows what the beam structure is. You should be able to make a distinction between beam and bar. So how do we make a distinction? That is, the simple rule is, forget about all the theories. Imagine that you are looking into something with some loads applied on it. What happens if the structure is made of a very soft material, something like a butter or cheese or something like that. And imagine under even a tiny load, how the structure would deform. That's the question you have to answer to yourself to make a decision. I mean, here I give you an example. Just simply by looking at the shape of a structure, you can't say whether this is a beam or bar. It also depends on the loading. So here on my right hand side, if I apply load outward, what happens is this elongates, or if I apply this axially, that would deform, shrink. So for that reason, this is classified as bar. The bar or two-force member is a simple member, is constituent of the truss structure. But for the very same geometry, if I support this from here, and either I apply a point torque or a point load or a distributed load, it doesn't matter. This is going to be a complex deformation. So whenever the deformation is something like a S, it's like a smiley, it's like crying, this is going to be a beam. So that is the basic rule for making decision. And once we are looking for the internal loads, there are three usual suspects. The first one is, let's say four of them, right? So first thing you want to find out is W of X. The next one is N of X. The third one is V of X. And the last one is M of X. So this is called distributed load. This one is called axial load. This is shear load. And this one is a bending moment. Okay, so we want to have a family album. So here at the top is the parent. So this one, I call this the graph of W of X. W of X versus X. The next is, maybe this is grandfather, this is the parent. This is N of X, X. The next one is V of X, X. And the last one is M of X, X. So why do we want to stack all these underneath? There is a good reason. Because there are some golden rules which are applicable to this problem. So well, first of all, N of X is not really important. That's something simple to take care of. But if we are strictly talking about the internal forces, yes, axial forces also is classified as an internal force. But in the case of the beam structure, the most important ones are V and M. So now you ask yourself why W of X is also a part of this family. The reason is, if we want to proceed from method of equation, W of X is the starting point. So you do need to have W of X to integrate, and by integration of W of X, you find V of X. And by integrating from V of X, you find out M of X. So that is why W of X is of paramount importance, because this is, if we get W of X wrong, all subsequential analysis would be wrong. So that is the basic things. And few things I want to mention here, that is the concept of the zone. The concept of the zone is whenever the load has a discontinuity, right? If I have a distributed load all over the beam, there is no discontinuity. But in this case, how many discontinuity are here? So there is one discontinuity here, one discontinuity of the moment here, one discontinuity of the distributed load here, one here. So if I want to find out how many zones are here, so this is zone 1, this is zone 2, this is zone 3, that is zone 4, and this is zone 5. So we have to split the beam into a number of the zones whenever the loadings are discontinued. So what is the meaning of discontinued? I mean, back to the algebra or calculus, that is when your plot is not continuous. The left limit is not equal to the right limit. And this is exactly what happens when you apply a point load. So the point load is like you're pushing something down, you're pushing it up, depending on the sign of the load. And the same thing happens with the distributed load. The difference is you are pushing this gradually. So all over the span of the distributed load, you're pushing this down or pushing it up. So when it comes to, so the first thing first, make sure your beam is labeled properly. If this doesn't have label, it is a must. You have to give label for every start or beginning of the zone. A, B, C, D, E, F. Otherwise, in writing the equation, definitely you make a mistake. So proper labeling is the key to a successful solution. Students always underestimate the importance of that. I mean, if you are not a good illustrator, you cannot analyze the structure. You should be able to draw free body diagram, just use some R, some mood. So otherwise, if you just want to make it simple, the chances are you make a mistake. So labeling is very important. Now, how many zones are here? There are 5 zones. For each zone, we have to see how W of X is defined. So can you tell me in the first zone what is W of X? No W of X, right? In the first zone, there is no distributed load. So over there, that is 0 distributed load. Whenever there is 0 distributed load, that means the shear force doesn't change. And why is that? Because method of equation is W of X is so integral of W of X dx is equal to delta V, or V of X minus V0. If for a zone W is 0, that means V of X is equal to V0. That means over the entire span, the shear doesn't change. Okay, so even without going through the equation, I know whatever the reaction here is, I have a positive reaction here. So between this zone, my shear force is not going to change. It remains constant. And then this point load is pushing this down. How much it takes on, it depends. It might get to here, it might go even below, or it might. And then between B and C, what is W of X? Again, that is 0, right? So it remains constant. Whatever the left limit was, the right limit becomes the same, and it comes all the way like so. And this is also the case in this zone. There is in the third zone, there is no distributed load. So whatever we had it in here, that will be continuous. So you might ask yourself, what about this discontinuity? This doesn't apply to the shear X. This applies to the bending moment X. So this is constant. The integral of a constant is a line. If this is positive, that would be a positive line. If this is negative, that's going to be a negative line. And when you get into a point torque like this one, you will have a jump. This is either jumping in a negative direction or jumping in a positive direction. So look into the convention we introduced. So according to that convention, this one is a from left hand side. So you're making in zone 3, you're cutting this here, right? So this one is making a This is -1. So that brings this down. So this continues push this down. And then from that point forward, whatever the integral is, that would be a positive line or negative line or that. So the last summary point is when you have to split your curves into pieces, there are two options. First is I want to introduce my zones. So here this is 2 meter, 2 meter, 2 meter, 2 meter, 2 meter. So altogether 1, 2, 3, 4, 5, 10 meter is the length of the beam. So when I'm writing my zones, there are two conventions here. The first convention is I introduce my zone number 1, x between 0 and 2. And when I try to write zone number 2, I can say x between 2 and 4. Or an easier approach is I say x is between 0 and 2. How come? Because in the second zone, I'm bringing my coordinate system here. And then that simplifies the integrations. That simplifies the integration. So if you want to keep x always pointing back toward the A, writing the equation sometimes is not straightforward. That makes the integration complex. Even in the case of previous method, which we use the free body diagram to get the same graphs, you could do the same thing. You could assume that always in each zone, x is reset at the start of the zone. That would simplify your definition of x and derivation of the relationship. So having all these summary in mind, now we can go back to do some examples. And like you asked, we start with something simple. So let me go back to page 535. All right, so let's take 11-1 or 11-2. Which one? Your choice. Number 1. Okay, let's do number 1. Okay, now we want to start. This is page 535. How many zones are here in terms of changing the loads? One zone. Yes, one zone is here. So the first task is to find out the reactions. So there will be a reaction at B and one reaction in opposite direction A. So I just got this by experience. It is okay if you assume both of them positive and later correct them. So here, a preliminary calculation, that is B of Y is equal to T divided by 6, which is 5 kilonewton. Is that clear? How did I do it? So I put 5 kilonewton here. And then this one is also 5 kilonewton. So there is one zone. So let's define the zone, zone number 1. That is X changes between 0 to 6. And then I would like to start from V of X. So this is my V of X. And the beginning is -5. And the end is +5. All right, so this one is starting by pushing, that reaction is pushing this 5 kilonewton down. And what is W of X here? What is W of X? Between 0 to 6, how the distributed load changes? 0, right? So because this is 0, and let me just write the equation for you. This is the key equation. You have to memorize it. That is V of X minus V of A is equal to integral of W of X dx between X equal to A to X equal to B. And because this is 0, I can conclude that V of X is equal to V of A, and that is constant. So therefore, my conclusion is V of X is equal to V of A and is equal to -5 kilonewton. How this can be interpreted? It means no matter what the X, the shear force would remain at -5. And now here, I want you to try communicating with this shape. I mean, that makes your life much easier. If you try just memorizing this one. So here, I'm starting at A. Suddenly, the reaction is pushing that down. So that is what I do. I'm pushing this down. How much? By the reaction, -5. And then this is constant between here and there, and suddenly here I have a reaction which is pushing this up. So pushing up means that brings my shear force to 0. So remember, if the beam has pin or pin roller, it always should have, because before the pin the shear is 0, after the roller the shear is 0. So here, that is just before the pin, and then the pin, no matter how many zones are there, if there are 2 pins or pin roller, it should start from 0, end with 0, the shear diagram. If that was a discontinuity in between, the discontinuity could push it up or push it down. All right, the next thing is we want to write an expression for bending moment. So bending moment, the formula is m of x minus m of a is integral of v of x dx between the same bound. And here, because this is -5, that is equal to -5x. But what is m of a? Is there a bending moment at the beginning? That's 0, right? So therefore, in this case, m of x is equal to minus 5x. So minus 5x means my second diagram, which is m of x. It starts at 0 and ends at minus 30. So just let's check this equation. If I want to check that, I have to check what is m of 0. M of 0 is 0. So this is 0 here. What is m of 6? X equal to 6. That is minus 5 times 6 minus 30. So it ends up to minus 30 Newton meter here. And how does it change? This is the equation of a line with a negative slope. And then what? How does it come back to 0 again? Because we have a positive things. I mean, this is according to convention, because you are looking into the left-hand side cut, and that one should bring back to 0. So there is a plus 30, which brings that to here. So this is shear force diagram, this is a bending moment diagram. And all it matters at this stage, we can pick up the maximum for the shear is minus 5. The maximum for the bending moment is minus 30. Later on, we can make a meaningful comparison to say which one is more critical, but not now. So, is there any part of it not clear? You want me to explain? You don't seem to? Yeah? Okay. So, let's move on to the next one, and we go there slowly, otherwise things become out of hand. So let's get the 11-2. All right, first thing first, we want to label this. And then I need someone telling me how many zones are here. One zone. And what would be the first step? The first step is to find the reactions. So to find the reactions, I'm going to have a vertical reaction here, and this is making counterclockwise. So there will be a clockwise reaction bending here. So that is 9 kilonewton here. And this one is 9 times 3, that's 27, right? So zone number 1, x changes between 0 to 3. So let's find out W of x. W of x, there is no distributed load. So for the entire span, W of x is 0. And V of x minus V of a, that is integral of W of x dx, which is equal to 0. Therefore, for the entire span, the shear doesn't change. The shear is V of x is equal to minus 9 kilonewton. So this seems to be quite similar to previous problem, isn't it? So here we have before that is 0, then -9, and it doesn't change over the entire span until just before point B, that is -9. At point B, the reaction brings -9 to 0. So if I want to illustrate that, this is like you are going down -9, and here you are going up +9, starting from 0, ending to 0. Okay, what will be the next step? The next step is to find an expression for m of x. So m of x minus m of a, that is equal to integral of v of x dx, which is -9x. So m of x is equal to -9x. So m of a, that is when x equal to 0, is equal to 0. M of b, this is just before b, right? Just before b. That is m of 3. That's -27. So again, starting from 0, it goes to -27. And then there is a discontinuity there. That discontinuity is a reaction which make this, the right hand side, make it 0. Yeah, that sign of the bending is quite confusing, isn't it? Can you? So if this one is, if you are done with that, or if there is any question. Okay, let's get 11-3. I start with labeling the shape. That is point A, this is point B. And in terms of the reaction, well, there will be one vertical reaction here, and then we're not sure whether the reaction here is clockwise or counterclockwise. Let's just put this as MB counterclockwise. And to solve this, I need to temporarily replace the distributed load with the resultant force. And the resultant force here is 90 kilonewton. Okay, 90 kilonewton, the line of action would be at the center. And to find B of Y, well, B of Y is equal to 90, yep. And then to find out the M of B, we take sum of rotation with respect to the B equal to 0. That is M of B plus 90 times 1.5 minus 25 is equal to 0. And $135 take away 25, that's 110. So M of B is minus 110. Is that what you found? So minus 110, that means I have to reverse the direction of M of B. And this one is 90. Okay, now we start with W of X. First of all, how many zones are here? One zone, yeah? So with that one zone, X is changing zone number 1. X changes between 0 to 3. And W of X, this is the trick. I'll be interested to see if people can pick W of X correctly. What is W of X? How can I write W of X as a function? $30 or minus $30. Yeah, this is, so I want you to remember this is extremely important. So we put the distributed load on the top simply for the sake of illustration. Just think this way. If I replace that one with a point load, that point load, is this going to be negative or positive? It's negative because it's pushing down. And can you give me an example where we have positive distributed load? Lift force under the wing in the airplane. So they are pushing from down up, upward. So those are examples of the positive distribution. We don't see them here quite a bit. I mean, in structural cases, most of the cases you have distributed load, but there's a roof. They're negative. So this is what students make a mistake. Even when you have a triangular equation, the maximum is negative something, is not positive something. When you are driving equation of the line, you easily can confuse this one by writing the equation. If that equation is written wrong, everything follows as mistake. Okay, so here you know why this is minus 30? And the unit is kilonewton per meter. Now, let me write, so maybe I don't need these portions just to save some space. Okay, now I write my equation as V of x, which is shear at the arbitrary point, any point inside the zone. V of x means shear at the distance of x measured from the left-hand side, minus V of a is equal to integral of W of x dx, and that is minus 30x, correct? And what is V of a? V of a is V at x equal to 0. So is there a shear force at the beginning? No. So that means V of x is simply an equation of a line, and this line has a negative gradient. And should be easy to plot. Yeah, after this one, definitely. Yeah, we will try to go from slowly. Yeah. So the shear forces start at 0, and then what is V of x at the end? That is V of b. Can we calculate V of b? Simply, all we have to do is V of b is V when you plug 3 as a x. So that is minus 90, right? Minus 90. So that means if I start from 0 here, that would gradually increase the shear in the negative direction to here, and suddenly I have a plus 90 here, which brings that back to 0. So starting from 0, ending at 0. So remember that pattern. The next is to find out the bending moment diagram. So this is V and this is M. So equation, this is something you have to memorize. M of x minus M of a is integral of V dx. And V is minus 30x, correct? So this is minus 15x squared. But what is M of a? Can anyone tell me what is M of a? 25. Is this positive or negative? That is positive, right? This is just if how can I justify that? Let's look at, I mean, we're just looking immediately after here, right? immediately after here, yeah, that is like the beam which we split into half, and then this is a splitting point, and then so this is positive, right? Was the positive convention. So this is resembling that one. This one resembling this one, right? So if this is positive, then we are starting from we are starting from 25, and then that equation, this is m of x is minus 15x squared plus 25. So m of a, that is when you plug x equal to 0, and m of b is when you plug x equal to 3. So what happens if I put x equal to 3 here? That is 15 times 9 plus 25. That's minus 110. Okay. So, do you remember how the parabola is? This is a quadratic parabola, and if it has a negative sign, that's like a reverse cup. Reverse cup doesn't hold water, that's negative. Upside cup holds water, that is positive. So that means it goes from okay, so that is how it is, and there should be a point where m of x becomes 0. That is x equal to root of 25 by 15. One 1.3. 1.3 meter. This is quadratic. And then we have a reaction which brings that back to 0 after. Okay, now as Fergus suggested, we go with something with shear changing. Okay, how is 11-4? Is this too simple or? Yep. All right. So let's start with labeling A and B. How many zones are here? One zone. Okay, so how do I find the reaction? The reaction is simple to find. Just remember, whenever there are distributed load, you have to replace it the point load resultant before you can calculate the reactions. So here, the resultant load should sit in 1 from the base, which is 1 meter from the base, 2 meter from the apex. And the area is 12 times 3 times 2 divided by 2. That is 3 times 6, 18, right? So it is 18. And that is 1 meter from there. So M of B is equal to 18 Newton meter. Correct? Okay, here is the challenging part. I want to write expression for W of X. Can someone help me with how the shape of this curve is? Is this a constant? Is this zero? Is this a line? Is this a quadratic or what? What is the shape of W of X? Is this a constant or a line or quadratic? Yeah. No, it is not quadratic. It is changing linearly. It is changing linearly. What is the general shape of a line? The general shape of a line is AX plus B, right? This is now all you have to do is to find A and B. How can we find them? Simply by noting that at x equal to 0, W is equal to 0. At x equal to 3, W is equal to what? 12 or minus 12? Minus 12. This is something easy to forget, right? I want to emphasize, don't forget this. We simply put them for the sake of illustration, for ease of illustration, but that shouldn't let us to mistake. All right, now let's plug this here. X equal to 0, that is A times 0 plus B equal to 0. So A times 0 plus B is equal to 0. That I conclude that B is equal to 0, right? And the second condition is let's plug X equal to 3. So that is 3A, B is 0 is equal to W of X, which is minus 12. So what is A? A is minus 4, right? Okay, now we are in the position to write expression. That is W of X is equal to minus 4X. All right, now I have W of X. It should be easy to find V of X. So the formula to find V of X is V of X minus V of A. That is integral of W of X dx. And that is minus 2x2. And V of A is 0, right? So therefore, V of X is minus 2x2. So let's check the numbers. What is V of A? Plugging X equal to 0, that is 0. What is V of B? V of B, that is by plugging X equal to 3, that is minus 2 times 9 is minus 18. All right, let's do the plot. So the plot is a parabola. So the parabola starts at 0 and it ends at -18. And then these reactions again bring that back to 0. How about m? M of x minus m of a is equal to integral of v dx, which is there is 0 bending at the beginning, so that vanishes. M of x is minus 2/3 x cubed. Okay, and that gives me the moment at the end. So the moment at the end should be m of 3 is minus 2/3 3 cubed, which is minus 2 times 9 is minus 18. So again, this one is a unimodal, doesn't have a minimum or maximum between 0 and 3, simply because if you take the derivative of that, that still only is maximum or minimum at the center. It doesn't have a peak in between. So that means you a very similar but from the quadratic order. Okay, if you want something fancy, that would be 11-5 or -6. You decide. Five. So add 2 letters to the begin and end, making the labelings complete. And to find out the reactions, let's replace the distributed load with the resultant. That would be 4 times 1.5 is 6. So because of the symmetry, we're going to have 6 and 6 here. All right. Now you tell me how many zones are there. 3, correct. There are 3 zones here. And let's start with zone number 1. X changes between 0 to 1.5. And we need an expression for W of X. How this expression can be written? Minus 4, right? Because the unit for that is Newton per meter. It's the intensity, it's not a load. The intensity of the load. That is minus 4. And then I want to write an expression for zone 1 that is V of X minus V of C is equal to integral of W dx, which is minus 4x. But what is V of C? Zero. That is just at the beginning, before we get into any distributed load. So this one vanishes. So V of X is minus 4x. And minus 4x, we can check. We can check V of A by plugging X equal to 1.5. So 1.5 times minus 4. That is, yeah, that is 6, right? Or minus 6, that is minus 6, correct? All right, that's interesting because all right, so here we start from 0. It goes to minus 6. And then there is a discontinuity. That discontinuity, this is pushing that back to 0, right? Minus 6 plus 6, it brings that to 0. And now let me move to the second zone. In the second zone, X, I would reset X from 0 again, between 0 to 3. So here, what is W of X in the second zone? 0. So that is V of A minus, sorry, V of X minus V of A is equal to integral of W dx, which is 0. Therefore, V of X is equal to 0. So that means between A and B, there is shear. The shear is 0. And let's move to the zone number, to the last zone. This is zone number 3. What is W over there? Minus 4, yes. And therefore, V of X minus V of B is equal to integral of minus 4 dx, which is minus 4x. And what is V of B? So please, this is something you easily can make mistake. When I say V of B, because there is discontinuity, do you have to take B before, at, or after? There are three adjacent points. 1B belongs to zone 2, 1B belongs to zone 3. So this is not continuous because you have a point load between. So here we are not talking about the one before, we are talking after, right? So here there is a +6, so this should be taken to 6 because we have discontinuity here. So it was 0 just before B. When you get at B, it is the right hand side. So I want you to understand this clearly. So how come this V is equal to +6? I'm claiming that V of B here is 6. Why is that? Because we are talking about zone 3, not zone 2. Zone 2, yes, V was 0, but in zone 3, because of that discontinuity, push that 6 up, that is equal to 6. So this is equal to 6, and therefore my equation becomes V of x minus 4x plus 6. And we can simply check this if I plug x equal to 1.5, because in this zone I reset the coordinates. Instead of making reference from the beginning, I made the reference at the start of the zone. So here I have to plug x equal to 1.5. That is V of CB is minus 4 times 1.5 plus 6 is equal to 0. Okay, let's plot the equation of this line. The equation of this line is from here you come back to 0. So starting from 0, ending at 0. Fergus, is this, do you follow that?
Yeah.
Sure, I can explain if you wish, but if you follow that, that's good. So I just wanted to note that when we are making this integral, you might, this is for zone 3. For zone 3, that starts from B to D. So how come at B we plot 6? Because before that V was 0. After that, because of this reaction, the 0 is shifted to +6. This is 6. So my point is, this is point B. There is a B minus. There is a B plus. B minus belongs to zone. B minus belongs to zone 2. B plus belongs to zone 3. And what you should use here, that is B plus. Make sense? All right, now let's follow for each zone to find out what the bending moment would look like. So in zone 1, we do have the V of x, so it should be simple to find. So that is zone number 1. M of x minus M of c is equal to integral of V dx. M of c vanishes, no bending at c. So M of x is minus 4x integral, that is minus 2x squared. So that means bending moment at point A, that is equal to minus 2 times 1.5 squared. So that is Yep, 4.5 negative. And the unit is kilonewton meter. So let's plot M for the first zone. So if I want to plot M for the first zone, that is a parabola. So this parabola starts from 0 and ends at minus 4.5. And let's continue with zone 2. Zone 2, that is M of x minus M of A. That is equal to integral of V d. For the second zone was what? That was 0. Okay, so that means M of x is equal to M of A is equal to minus 4.5. So in the second zone, we have bending moment constant. And what happens in the third zone? Third zone, that is M of x minus M of B is equal to integral of V dx. So what is V of B? M of B. M of B, because there is no discontinuity here, B minus B plus have the same magnitude of the bending moment because there's no external torque over there, right? So that is M of x minus 4.5. This is plus 4.5 is equal to integral of this guy here. That is equal to minus 2x2 plus 6x. And then that one, I should take it to the right-hand side. So M of x for the third zone, that is minus 2x2 plus 6x minus 4.5. So if I plug x equal to 0, that is minus 4 point. And if I plug x equal to 1.5, that is M of d. Plus 6 times 1.5, yeah, minus 4 point, that's 0, right? Bending moment at the end is 0. That makes sense, doesn't it? Because the end is free. So M at the end is equal to 0. So again, this is a parabola, the parabola which finishes like so. So this is a very good example. I mean, make sure you keep this one for your summary. If you can understand all the steps here, you are out of the wood. So we could go to something a little bit more mathematical. It's up to you. I mean, 11-6 is more mathematical. Do you want? Yeah, why not? Let's try that. Okay, so in terms of labeling, it is all labeled well, doesn't need any extra work. It's just we do need to have reactions calculated. So how do I go with the reaction? I have to replace the distributed load with the resultant, and these resultants are sitting where? They are sitting 1/3 from the base, 2/3 from the apex, and they are each 10 times 3 divided by 2, which is 15. 15 kilonewton, and this is 15 kilonewton. And therefore, because of the symmetry, this is 15 kilonewton, this is 15 kilonewton. All right, how many zones are here? How many zones, Fergus? How many zones? How many regions? 2, yes? So zone number 1, that is x between 0 to 3, that is point C is between x of A and x of C. And now we have the most challenging part of this problem is to identify W of x for this zone. How do I write this one? Is this a constant, linear, quadratic? What type of form does it have? It's a linear, right? So linear means I need to identify A and B. So I start with writing W of x as AX plus B, and then 2 boundary conditions. The boundary condition is when x is equal to 0, what is W then? At A. What is W at A? No, that is A. I'm talking about zone 1. Sorry, I don't get it. So at point A, W of x, what is it? No, this is A. This is A. So it starts from here, goes to 0. But at the beginning, it's not 0. That's the starting point. The starting point is minus 10. Minus 10. Minus 10. Yeah. I don't know why everyone makes this mistake. It's yeah, minus 10. And when x is equal to 3, what is W of x? 0. Well done. Now let's apply these 2 points inside that line to find A and B. So I put minus 10 as W of x is equal to A times 0 plus B. And that gives me B equal to minus 10. And then I try equation, the condition number 2. that is x equal to 3. So this is 0 w of x is equal to a times 3 plus b. b is minus 10. So therefore, a is what? A is 10 over 3. Correct? Now we can write down w of x is 10 over 3x minus 10. So this is something you have to practice. That is a key point because this is a starting point. We can't get the starting point wrong. Okay, Sean, can you hear me well? It seems my line is dropping temporarily. Can you hear me, Sean? Okay, good. Or maybe, yeah, if you have problems, just stop me. I would reconnect and fix this. But if you can hear me well, no, that's good. All right, thank you, Sean. And right, so this was all to find w of x. And it would be a good exercise for the next zone. You drive the w of x yourself, but just bear with me. Maybe we do this later on. For now, let's just use what we achieved, which is w of x equal to this. And now that I have w of x, it should be simple to write an expression for v, because v of x minus v of a is equal to integral of w dx, which is 10x squared by 6 minus 10x. But what is v of a? V of a is minus 15. Minus 15 minus is plus 15. Take it to the right hand side, that is minus. So v of x is 10 over 6 x squared minus 10x minus 10. So you can check this one by putting x equal to 0, that's minus 10. Yeah, that is v of a is positive. Yeah, that becomes minus. You're right. So that is minus. This side is positive. Sorry? 15, yeah, 15. But 15 is correct, yeah. So v of a becomes v of 0, that is 15, and v of 3. What is v of 3? 9 times 10 divided by 6 minus 30 plus 15. That's 0. So in the middle, your shear becomes 0. All right? And this is a quadratic. This is a quadratic. So this is v of 3 is equal to 0. Now let's plot the first zone. For the first zone, So it starts at 15 and then goes to 0 in a quadratic way. That means there must be a minimum maximum in between, right? So this is quadratic curve. We want to plot it. So we do have one point here. The second point is here. No, sorry, the first point is here. Second point is here. But what happens between here and there? There should be a maximum. How do I find that maximum? Is by setting the derivative of this one equal to 0. The derivative set to 0, that is that is w of x, isn't it? This is how it changes. There's no maximum minimum between. There's no maximum minimum between. That changes quadratically like so. And how about m of x? Minus m of a, that is equal to integral of v dx, which is that is 10 divided by minus 5x squared plus 15x, correct? And m of a is 0. There is no bending moment to begin with. So therefore, m of x is so we can test this one by plugging x equal to 0, that is m of a, m of 0, that is equal to 0. And what about m of the middle point was called what? C. Yeah. So m of c is m x equal to 3. So that is
Last two terms cancel each other.
yeah, you can cancel that. This is yeah. I'm just lazy. Let me use a calculator. My brain is on a strike now. $15. Is that what you found? Okay, thank you. That is positive 15. So it means we have a cubic which starts from 0 goes to 15. I'm not sure if that goes in a this way or that way. Um, yeah, that we have to check. I'm not sure. This is 15. And then we take the same thing with the zone 2. So zone 2, can I ask everyone, assuming that x starts from 0 to 3, can you identify an expression for w of x in zone 2? Let's try. Yeah, let's try that. Maybe I'm just saving some space here. Okay, zone number 2, x changes between 0 to 3, and that is x of c and x of b. So here we have two pairs. At x equal to 0, what is w? x0, what is w in the second zone? We're talking about w. At this point, what is w? Point C. 0. Yeah. And x equal to 3, what is w? Negative 10. So if I write my expression as w of x equal to ax plus b, I simply try this point. So 0 is equal to 0 plus b. That gives me b equal to 0. And then minus 10 is equal to a times 3. So therefore, a is equal to minus 10 over 3. So therefore, your w of x minus 10 over 3x. Is that what you got? Guess? Okay, good. Now let's take it from here. V of x, this is the second zone. V of x minus V of c is equal to integral of w dx, and that is V of x minus, what is V of c? There is no discontinuity in shear, so c minus and c plus are equal. So because that c minus shear is 0, c plus is also 0. Minus 10 over 6 x squared. All right, so that means V of x is equal to and x equal to 0, that's x of c. V is equal to 0, and V of 3, that is minus 15. Okay, so that is an equation of a line. This is a This is a parabola, and the parabola is changing like so. Okay, top of my head, in the last term, we had something like this in the final exam. Okay? Well, yeah. In the exam, I think this one was a multi-choice question. Give you 4 figures, and you don't have to worry about the numbers. You have to just make a judgment about the shape. Shape is, this is linear, that one should be quadratic, the next one should be cubic. This is 0, the next one should be constant, the next one should be line. Judgment like that. No calculation is needed. Simply, if you know the basic, you should be able to choose the right. Multi-choice doesn't need you to present your workout. It's either you can toss a coin, and then if that's right, you get the mark. We only ask for the written solution for analytical problem, not for the multi-choice. Okay, now let's see whether the bending is also simple. So if I want to find the bending moment in the second zone, m of x minus of c is equal to integral of v dx, and m of c, because there is no discontinuity of the bending moment in the between, c minus and c plus are equal. So here mc is plus 15. Okay. So this justification is the key ingredient. If you want me to explain that more, don't be shy. So I'm happy to explain. So in each case, when you go from one zone to another zone, you have to make a decision whether whatever that point is, point B, B minus, B plus, are the shears equal on both sides? Are the bending moments equal on both sides? To answer that question, just look at the loading. If the loading has a discontinuity, they are not equal. If there is no external load between the transition of the zone, then point minus is equal to the point plus whatever shear or bending. Or here in this case, the bending moment at point C MC minus should be equal to MC plus because there is no discontinuity. So therefore, in that equation, I'm plugging that as positive 15. So that is mx minus 15 is equal to integral of that expression here, which is minus 5 over 9 x cubed. And therefore, m of x is what? Minus 5 over 9 x cubed plus 15. If I plug x equal to 0, that is plus 15. If I plug m equal to 3, that is also 0. Okay, and that makes sense because end point is a pinpoint. Pinpoint, you can't have any non-zero. Here the moment should be 0. So that means
In the end, you have to run symmetrical.
The one which I gave you, that was symmetrical, and yeah, this is, I think that was exactly the same one. So if I want to put all the, you don't need a snapshot, do you? If you want, I can organize this one for a snapshot if you wish. Okay, so let's take a attendance and then we see. Okay. Art is here, Flynn away. Art is here. Kate is here. Ferg is here. And Sean away. Sean away. Ivan is here. And Charlie is online. All right. We continued study of the internal loads. When there is a beam, there are three internal loads, or three internal expression of X. The first one being distributed load W of X, second one is V of X, the third one is M of X. And they are related through integral relationship. So depending how many loading zones or discontinuities are there, we have to decide how many regions, how many zones. For each zone, we start from W of X, integrate, that gives you V of X, integrate, that gives you M of X. Everything else is a little tricks with the boundary conditions, and I suggest if you are rusty with the graphs, go back to the high school, just have a look at how did you draw a line, how did you draw a quadratic, cubic, that would help. No. No. All right, any question? Thank you very much, being such a wonderful audience. Have a great weekend. Enjoy. Enjoy.
Have a good weekend.
You too. Thank you, Sean. See you. Any questions, Sean? All right, thank you. See you soon. Bye.